The production of 408,386 vehicles in Q1 2026 is merely the tip of an iceberg for a revolution quietly unfolding at Giga Texas, powered by the 50,000-ton Gigapress and the unboxed process. As printing cars becomes a reality and third-generation LFP batteries slash
costs by 50%, Tesla is not just leading the market, it is executing a global takeover. Now that technology enables the leap from hundreds of thousands to millions of vehicles seemingly overnight, will the legendary names of Detroit and Wolfsburg realize they've been left behind before it's too late? 1. The world's only 50,000 tons Gigapress. You may have heard about Cybercab and the unboxed process, but if you look more closely at April 2026, when Cybercab officially enters mass production, you'll realize this is not a story about a new car. This is the moment when the 50,000-ton Gigapress is truly operating at industrial scale for the first time, triggering a chain reaction that could reshape the entire automotive industry. According to Elon Musk, this marks the next major leap beyond gigacasting.
The numbers alone are astonishing. A force of 50,000 tons, roughly 50 million kilograms, compresses molten aluminum into a single structural component in just milliseconds. Compared to the 6,000-ton presses used for Model Y and the 9,000-ton system used for Cybertruck, this represents a significant
scale increase of approximately 8 times and 5 times, pushing die casting into an entirely new industrial domain. Each casting cycle is expected to take only a few minutes, meaning that in theory, a single machine could produce hundreds of large structural components per day. From a competitive standpoint, rivals remain far behind this level. Companies like XPeng are currently operating presses around 16,000 tons, while traditional automakers such as Ford and Toyota are still experimenting with 6,000 to 9,000 ton systems for next-generation EV platforms. With Cybercab, Tesla is not simply scaling up, it is effectively creating an entirely new manufacturing category, making even its own previous systems, such as Model Y 6,000 tons and Cybertruck 9,000 tons, appear technically small in comparison.
But what does this actually change? Traditionally, a car body is a complex system consisting of around 200 to 300 individual stamped parts joined together by thousands of welds. Each weld introduces potential defects, and each component adds cost, logistics, and supplier dependency. The 50,000-ton Gigapress eliminates this complexity by casting large sections, potentially the entire underbody, in a single shot. Molten aluminum, heated to approximately 700 to 800 degrees Celsius, is injected into a massive mold and pressed under extreme force before being rapidly cooled to maintain structural integrity at the microscopic level. The result is not just fewer parts, but the elimination of entire production stages. This transformation directly impacts the supply chain. By removing hundreds of components, Tesla reduces reliance on dozens of Tier 1 and Tier 2 suppliers, particularly those specializing in stamped steel, welding systems, and subassemblies. Instead, demand shifts toward high-performance aluminum alloys, ultra-durable casting molds costing millions of dollars each, and advanced thermal management systems capable of handling extreme heat cycles. In other words, Tesla is not just simplifying production, it is rebuilding the supplier ecosystem around itself. This casting breakthrough integrates tightly with Tesla's unboxed manufacturing system. Instead of a linear assembly line, Tesla produces 5 to 6 major modules in parallel, including the front, rear, structural battery pack, and side structures, before assembling them in a final step. This system reduces factory footprint by 40% and labor costs by 30%, while cutting the total number of parts roughly in half compared to the Model 3.
Combined with the elimination of the paint shop, traditionally the most energy-intensive and space-consuming part of a factory, Tesla is compressing what was once a massive industrial process into a far more compact and efficient system. Paint shops alone can account for 20 to 30% of total factory energy consumption, and Tesla is effectively removing that entirely by using pre-colored polyurethane panels. But this is where the narrative shifts, and the risks become unavoidable. What happens when everything depends on a single machine? The 50,000-ton gigapress introduces a critical single point of failure. If this machine goes down, the entire production line, potentially producing thousands of vehicles per week, could come to a halt.
Unlike traditional assembly systems, where issues can be isolated and bypassed, this level of integration concentrates risk into one asset. Considering Tesla's target of producing one Cybercab every 10 seconds at peak capacity, even a few hours of downtime could result in thousands of lost units.
Then there is the issue of defects. At this scale, even the smallest imperfections, such as air bubbles, uneven cooling, or micro cracks, can compromise the entire casting. Industry defect rates for large-scale die casting can range from 1% to 5%, but at Tesla's target of up to 2 million vehicles per year, even a 1% defect rate could result in 20,000 unusable castings annually.
Then there is the issue of defects. At this scale, even the smallest imperfections, such as air bubbles, uneven cooling, or micro cracks, can compromise the entire casting. Industry defect rates for large-scale die casting can range from 1% to 5%, but at Tesla's target of up to 2 million vehicles per year, even a 1% defect rate could result in 20,000 unusable castings annually. With ambitions of producing 2 million Cybercabs annually, combined with 6.9 billion miles of full self-driving data supporting its autonomous platform, Tesla is not just building a car, it is building a large-scale autonomous mobility system. Early production signals already support this trajectory. Drone footage has shown around 14 Cybercabs in outbound lots with 25 completed units observed earlier, and hundreds more in various stages of production. This indicates that the system is moving from validation to early scaling. But the deeper question remains: when a car is reduced to a single casting formed under extreme force, does it become the ultimate expression of manufacturing efficiency, or a system so optimized that even the smallest failures become exponentially more costly? 2. The peerless unboxed assembly process. For over a century, Henry Ford's moving assembly line has dominated the manufacturing industry. However, as we enter 2026, Tesla has officially obliterated this concept with its unboxed process. Far from being just a concept on paper, two key patents are actively transforming gigafactories like Giga Texas into Colossus. Below is a detailed analysis of the parallel assembly process, the secret behind Tesla's 50% reduction in production costs. The first pillar of this revolution is skateboard-first structural assembly, which fundamentally rethinks the vehicle's foundation. In a traditional plant, the chassis is a passive, empty cage. In the unboxed world, the production begins with the skateboard, a structural battery pack that serves as the vehicle's floor and master reference point. By attaching pre-assembled front and rear modules directly to this open floor, Tesla eliminates the need for a protective shell during the most labor-intensive stages of construction. The physical difference is staggering. While a Toyota or Volkswagen line requires robots to navigate through door or windshield apertures, a process fraught with collision risk and slow cycle times, Tesla's robots have 360-degree top-down access. Imagine the difference between trying to build a ship inside a bottle versus building it on a wide-open, dry dock. This architectural freedom allows for a density of automation that was previously impossible, potentially increasing robot per square meter efficiency by over 50%. This spatial freedom enables the second core innovation, preloading components. Tesla has decoupled the assembly process into 3 to 5 independent production lanes that run simultaneously. While the rear module is being fitted with drive units and suspension, the front module is concurrently receiving its steering rack, cooling systems, and fully tested dashboard. The most radical change, however, is the interior. In 2026, the Cybercab seats, carpets, and center consoles are not stuffed into the car. They are dropped vertically onto the open skateboard by overhead gantry robots. This eliminates the risk of interior scratches and allows for subassemblies to be fully software validated before they ever meet the chassis. This parallel workflow is the industrial equivalent of multi-core processing in a CPU. Tasks that once took 10 hours in a rigid sequence are now compressed into a 6-hour simultaneous burst. As of Q1 2026, the data confirms that this transition is no longer a theoretical exercise, but a market reality. Tesla reported producing over 408,000 vehicles in the first quarter alone, maintaining a lead in manufacturing efficiency that has forced legacy rivals into a state of paralysis. At Giga Texas, where the unboxed method has been pioneered for the Cybercab, Tesla is targeting a blistering cycle time of just 10 seconds per vehicle. This is a quantum leap compared to the 30 to 60-second cycles common in the best traditional factories. By achieving a 40% reduction in factory footprint and a projected 50% reduction in production costs, Tesla is effectively printing cars in modular chunks, allowing them to target a $25,000 to $30,000 price point for fully autonomous transport while maintaining healthy margins. The final closing the box phase is the master stroke of the entire operation. Only after the skateboard, front, and rear sections are fused and the interior is fully populated do the two side panels and the roof get attached. This sequence allows Tesla to bypass the traditional paint shop bottleneck. Instead of sending a massive complex shell through energy-intensive e-coat tanks and ovens, only individual flat panels are treated. This drastically reduces energy consumption and provides a significant ESG advantage in strict regulatory environment. Tesla is not just updating a factory, they are deleting the assembly line as we know it, proving that the body in white was never a necessity, it was a limitation. As Tesla prepares to flood the market with high-margin, ultra-efficient cybercabs, a haunting question remains for every other CEO in Detroit, Munich, and Tokyo. If your competitor can build a more advanced vehicle in half the space and half the time, using a process your current factories are physically incapable of replicating, how much longer can you afford to keep building boxes? 3. Third-generation LFP battery technology. Tesla has added Sunwoda as its fifth global battery supplier in a clear move to cut costs and strengthen supply chain resilience by reducing dependence on cattle and shifting from buying fully assembled modules to sourcing raw prismatic LFP cells. Tesla gains tighter control over battery costs and production. But beyond supply strategy, the real focus is the technology itself. Third-generation LFP batteries that could redefine performance in Tesla's mass-market vehicles. At the core of this upgrade is Gen 3 LFP chemistry combined with a prismatic cell design. Unlike cylindrical cells, prismatic cells use a rectangular structure that improves space utilization inside the battery pack, allowing more active material to be packed into the same volume. This directly enhances pack-level energy density without significantly increasing cost. More importantly, the internal chemistry has been optimized to reduce resistance and improve ion flow, which is critical for enabling higher charging speeds. These improvements allow the battery to safely operate at a 3C charging rate, meaning it can theoretically charge in about 20 minutes, 3 times faster than traditional 1C systems. Compared to Tesla's current LFP batteries, which typically operate at 1C to 2C, this represents a major leap. In real-world conditions, charging from 10% to 80% could drop from around 30 to 40 minutes to closer to 20 minutes. That is a decisive improvement for entry-level vehicles, where charging time has long been a key limitation. Instead of being seen as the cheaper but slower option, LFP batteries are now approaching the convenience level of premium chemistries, making them far more viable for mass adoption. What makes Gen 3 LFP particularly strong is not just peak charging speed, but charging stability. High-nickel NCA batteries can reach peak power levels of around 250 kW at superchargers, but that performance quickly declines as the battery fills. This creates a steep charging curve where average speed is much lower than the peak. In contrast, LFP chemistry offers a flatter voltage profile and higher thermal stability, allowing it to maintain a more consistent charging rate across a wider range of state of charge. The result is a faster and more predictable real-world charging experience, even if peak numbers appear similar. Thermal performance is another major advantage. LFP batteries are inherently more resistant to overheating and thermal runaway, which reduces the need for complex cooling systems. This not only lowers production cost, but also improves reliability and safety with fewer cooling components required. Tesla can simplify pack design, reduce weight, and increase manufacturing efficiency. At scale, these small optimizations compound into significant cost savings across hundreds of thousands of vehicles. Durability further strengthens the case for Gen 3 LFP. While NCA batteries typically last around 1,000 to 1,500 full charge cycles, LFP can exceed 3,000 cycles under normal conditions. Even with higher charging speeds like 3C, the improved chemistry helps maintain long-term stability, meaning users get both faster charging and longer battery life. This combination is especially important for Tesla's strategy in lower-cost vehicles, where total cost of ownership is a key selling point. However, despite these clear improvements, the competitive landscape is evolving rapidly. In China, companies like Zeekr have already introduced LFP batteries capable of 5.5C charging, enabling 10% to 80% charging in under 10 minutes. This sets a new benchmark that goes far beyond Tesla's current 3C capability. It highlights how quickly the standard is shifting from 30 minutes to 20 minutes, and now towards single-digit charging times. This is exactly why Tesla's partnership with Sunwoda is strategically important. It is not just about adopting 3C technology today, but about positioning Tesla within a fast-moving battery ecosystem where future breakthroughs are happening. The current generation of LFP batteries is a stepping stone, allowing Tesla to improve cost and performance now while preparing for even faster charging technologies in the near future.